As we said in the previous video, we're going to pick up here with sp3, which seems like it would be a little bit more complicated issue. But it'll help if we visualize CH4 as living in Cartesian coordinate space, where carbon is at the center, is at the origin, and that would give us 8 quadrants. There would be the quadrant where all 3 coordinates are positive, so the positive x, positive y, positive z direction, and then opposite that there would be the negative direction, and then there would be positive x, positive y, negative z, and then opposite that negative, positive, and so on. You can see these written out in the notes. So each of these orbitals would exist 45 degrees out into one of those quadrants from the nucleus, and so there'd be 4 quadrants that would have an sp3 orbital in them, and the 4 that are exactly diagonal from those would not have an sp3 orbital in them. So for example, if we put an orbital in the positive direction, it would be the same amount positive in the x, y, and z direction, so we can leave all of these equal to one another, and it would be and it would eliminate the negative direction. And so if we have negative positive, we wouldn't have positive negative. If we have positive negative, we wouldn't have negative positive, and that leaves us with just negative negative instead of positive positive. Now, as far as the coefficients are concerned, all 4 of these orbitals are hybridized with the same amount of s, and so the sum of this coefficient plus this one plus this one plus this one, each of them squared, has to add up to 1. So that means that each of those c squareds is 1/4, and the square root of 1/4 is 1/2. So each of these coefficients is 1/2. But these 3 have to be equal to one another as well, and the squares of all 4 of these have to add up to 1. And so the only way to do that is for all of these to be square root of 1/4 or 1/2. And that's why we've written it this way. So this is one possibility for a wave function for the hybridized orbitals on a carbon, on a CH4 molecule. Now, something to bear in mind is that this is just those atomic orbitals. It's not wave functions for the molecule. In order to set up a wave function for the whole molecule, we would have to take these 4 orbitals that we've constructed, as well as the 1s on the carbon, as well as the 1s on each of the hydrogens, and build a Slater determinant with them. And so, again, I won't have you write all that out, but that's what Gaussian is doing if you ask it to solve a Schrodinger equation for a CH4 molecule. It's taking the Hamiltonian that we constructed earlier, it's taking a wave function set up like this, making a Slater determinant with this set of wave functions, as well as the hydrogen 1s's and the carbon 1s, and then starting to perform an iterative calculation where we minimize the energy by altering the zetas that replace the z's in the Hamiltonians, and beginning to alter these coefficients in ways that still keep normalization valid, but lower the energy. And we go back and forth until we get to the lowest energy possible. Is there any other option besides this one? This one's fairly easy to put together, but might not be as easy to visualize for some of you. Is there any other option for a valid starting set of sp3 orbitals? Well, let's see if we can think of one. In this next situation, we're going to allow psi A to just be entirely along the z-axis. So we're setting up so that one of our sp3 orbitals is along the z-axis. Another one, so that's going to be up. It's only going to have z contribution to it, and s contribution to it. And so the other three are going to have negative z contribution to them because they're going to be downward from the nucleus. And this one won't have any x contribution to it. So the neat thing about the math here is that the square of this and the square of this have to add up to 1. All right, the square of this is 1/4, so the square of this has to be 3/4. So this is square root of 3 over 2. And so we know what that is automatically. And then the other three of these have to be equal to one another. We have negative signs there because they're in a downward direction. And the square of this one, which we just said the square of this one is 3/4, and the square of these three each have to add up to, all have to add up to 1. And so these each have to be the square root of 1/12. I'll let you work that out mathematically. But that leaves us in a position where it's pretty easy to figure out this one. Because this squared is going to be 1/4, this squared is going to be 1/12, and so 1/4 is 3/12, so that adds up to 4/12. This has to be the square root of 8/12, or the square root of 2/3. And notice that this one is only in the xz plane. There's no y contributions. These have to be equal to one another then. One of them is moving out in the positive y direction, the other one in the negative y direction. And so the rest of the math can be figured out fairly simply through normalization and symmetry. And so on the next slide I will post, let's get my head out of the way, I should have done that a minute ago. But on the next slide I'll post what those look like. I had said this one was square root of 3 over 2 or square root of 3/4. We have square root of 2/3 here like we said. And then the sum of the x's all have to add, the sum of the squares of the x's all have to add up to 1. So if this square is 2/3, then these each have to be half of 1/3 or 1/6. So the coefficient ends up being square root of 1/6. And you can double check to make sure that these are each normalized in the horizontal direction, and then that they normalize in this direction as well. And so there's two options that a computer could use depending on how you built the geometry of the molecule to deal with a symmetric sp3 situation. So this would work for CH4, CF4, CCl4, and so on. But what we haven't dealt with, that we're going to deal with primarily in the next video, is a situation where we have a hybridized carbon orbital and the ligands that are attached to it are not all identical, so we can't just assume that the bond angles are going to be exactly 109 and that we're going to maintain all of that symmetry that we've talked about before. If the bond angles are known experimentally, the contraction coefficients can be adjusted using trigonometry to fit orbitals to the known angles. When the bond angles are not known, a qualitative approach can be used to give a starting geometry. And then that same variational procedure we just described a few minutes ago can be used to optimize the geometry. And so those guidelines, those qualitative approaches that we'll use are going to be described primarily in the next video, where we'll define the Henry Bent guidelines. I'll post those here before we move on, but we won't have time to run the mathematics of it out in this video. And so we'll start the next video with this slide that describes the Henry Bent guidelines. Central atoms are classified as either sp3, sp2, or sp, based on the rules you learned in Gen Chem. Ligands are classified as electropositive or electronegative. Lone pairs are electropositive, more so than any ligand. The more S character from the central atom is going to concentrate toward electropositive ligands, and more P character is going to go toward electronegative ligands. And electronegative means what it meant in Gen Chem. Fluorine is more electronegative than chlorine, and so on. So we'll try out a couple of examples of this in the next video.